Welcome to Soundside. I'm Gabriel Spitzer. It's been quite a week for one Seattle scientist after getting an unexpected late-night call from a Swedish phone number last week. That call turned out to bring good news. Mary Brunkow is sharing this year's Nobel Prize in Physiology or Medicine. She's being honored for research she did decades ago, work that would eventually loom large in developing ways to treat autoimmune disease and cancer. We invited Mary Brunkow on the show to reflect a bit on what that work looks like in hindsight and what it means to share this honor. She joins us now. Dr. Brunkow, welcome and congratulations.
Good morning. Thank you very much.
So it seems like your story starts in a lot of ways with this sort of strange mouse. Can you tell us about this oddball mouse and what was intriguing about it, why it was an interesting scientific question to tackle?
Yeah, so this mouse is called the scurfy mouse, which was kind of based on the appearance of it. And it was a naturally arising mutation that was observed at the Oak Ridge National Laboratories, which has a really top-notch mouse genetics group and pathology group. And they noted this mouse because it has a really profound autoimmune phenotype. And so, and basically that's all, except, it's a really specific disease that affects the immune system, and so seemed really critical and might be something that would be really useful for also understanding the human immune system.
Well, so you've had this curiosity, kind of, this one particular lineage of mice out of a national laboratory that had an interesting looking mutation. What was it that you brought to the table that was able to sort of nail down what was behind it, whereas others had not been able to before?
Well, I was working at a small biotech startup company up in Bothell called Darwin Molecular, and the focus of the company was really in identification of new drug targets, mostly in the world of immunology, but we were also in some other fields as well. But we had a really top-notch immunology group as well. And through collaboration with the Oak Ridge National Labs, we got access to the scurfy mouse, and we had access to the resources and technologies and whatnot to pursue the actual identification of the cause of the disease. And, our hope, of course, was that would lead to a good drug target. And what I brought to the table was experience in mouse genetics and molecular biology, molecular genetics and genomics. And so I oversaw the strategy for fine mapping of the locus, and then all of the kind of what we called positional cloning at the time. This was at a time when, the Human Genome Project was in full swing, but it was far from being finished. And the amount of genome sequence or, chromosomal sequence that was available at the time was really minimal. So it was not an easy task to link a genetic map, which is based on, like recombination events between chromosomes, link that to an actual physical map, which is, the exact DNA sequence. So we had to do a lot of tricks and whatnot, and we definitely took advantage of every kind of research reagent that was available at the time to help us piece together a really detailed and accurate map and then exact sequence across a pretty large region of the X chromosome. And then finally found the mutation in the mice, which is just a 2 nucleotide deletion. So it was a real needle in a haystack search.
Yeah, can you say a little bit more about that? Give us a sense of the scale of the haystack that you were searching in.
The first step was to set up a large breeding experiment, actually, with the mice, and doing genetic mapping to keep honing in closer and closer into the locus based on recombination sites on the chromosome. So that's the genetic mapping side of things. And at the same time, we were also, we could sort of identify molecular or, real DNA-based markers across the region, which started to give us some idea of how big physically the region was. And when we convinced ourselves that we were probably we had localized it to as small a region as manageable, it was about 500,000 base pairs.
That's considered manageable?
It was, these days it would be totally manageable, but in those days that was pretty daunting still. But that's kind of that's the point at which we really went crazy, developing a physical map across the region and then doing our own in-house sequencing across the region. And all the time we were of course keeping an eye on the data that were coming out of the Human Genome Project. There was some X chromosome specific data that we could get our hands on, and we used what we could, but it was but in the end, we really had to generate our own really high quality sequence across that mouse X chromosome region. And in that 500,000 base pair region, there were about 20 genes, we estimated. Some of the genes were known and had already been reported. Some of the genes were totally novel, but were predicted by, the computer algorithms that were available at the time.
So, okay, once you did locate the gene and you were able to clone it, confirm that you had the right one that was responsible for this weird autoimmune disorder that these mice had, what happened next? That obviously gets sort of, released out into the world in terms of the scientific ecosystem, and people run with it. What did you do with it after that? Anything?
Well, first of all, importantly, we connected with clinical researchers at the University of Washington and OHSU who were studying immune diseases in children and humans. And there was an X-linked autoimmune condition in humans that looked very similar phenotype-wise. And so they had DNA samples that they had collected from affected families over the years, and we were in fact able to identify novel mutations in the equivalent FOXP3 gene in humans, which was, tremendous confirmation that we really had the right gene. And it also really helped, of course, the clinical researchers to, at least gave them a handle to pursue additional analysis of the condition.
So one of the places that this led was the discovery and characterization of this class of immune cells, right? These T cell regulators. Did you see that coming when you were doing the mouse work?
I should say that my background was not in immunology. And in fact, I find immunology pretty intimidating. It's an extremely complicated field of biology. And so that's where I was very lucky to have these talented immunologists in the lab right next door. And they were, even before we cloned the gene, they were doing a lot of different kinds of assays on the scurfy mice that gave them a lot more of a, detailed picture of what exactly was going on, what could possibly cause this autoimmune phenotype. And at the same time, in the literature, there was kind of a hypothesis or a postulation that there had to be some kind of regulatory T cell, but nobody could really get a handle on the cells themselves because they represent quite a small subpopulation. And they also have markers that are in common with normal T cells. So it was really hard. It was like, we know there are regulatory T cells out there somewhere, but we don't have a way of capturing them and studying them. And so the FOXP3 gene is exquisitely specific to T cells, and subsequent work showed that it really is the key driver for making T cells go down the regulatory pathway.
Your work, the big paper that you published and some of the subsequent work, I mean, this all dates back to the late 90s and the early 2000s, right? What's it been like to sort of get this award now for work that you did more than 2 decades ago?
Well, it's overwhelming. And I have to say, we at Darwin, and then we became Celtech when we were acquired, we knew we were doing something important and we would still be working on it today, except that the company closed its doors in 2003. So for me, my career has, gone in other directions, and I have kept a sort of, peripheral watch on how things have progressed in the field. But with this recognition from the Nobel Committee, it's been a real honor and a privilege to go back and look more closely at exactly how that discovery has really had quite a significant impact, of course, in the way that we think about autoimmunity and cancer and organ transplants and all kinds of things. So it really is a discovery that, at the time we knew it was important, but of course, important discoveries are made all the time. And this award is recognizing the, huge impact, because it really opened a new way of looking at the immune system and a new way to really get a handle on these regulatory cells.
Yeah. And I'm just curious what it's been like for you personally or even emotionally to sort of be back in that period of your life and career and be immersed in that time. What's that felt like?
Well, it's overwhelming. It's been a pleasure to think back to those days, because it was a fabulous time in my life. We were all working so hard, and I worked day and night, and had a fabulous team working with me to help solve the cloning problem. And it was a great time, because we had really good support also from the company itself. But we were just a small little operation, mighty and productive. And then it all changed quite rapidly when the company closed down. So it's been quite an experience, emotionally but also exciting to really take stock of how it has impacted, human health, which, I couldn't wish for anything better.
We seem to be moving through a rather different kind of era at the moment when it comes to big science and fundamental science. I wonder what your story has to say, you think, about the value of doing basic science.
Well, it's absolutely critical. You have to. And we were in a somewhat unusual situation in that we were in a company. We were not, an academic group, which is typically where this kind of work would be done. But we certainly benefited from all of the work. Basic science is always building on what came before. And most of the discoveries in immunology, have come out of academic labs over the years. And certainly everything that's been done after our discovery, much of it would be done in academic labs. And at the time that the work was done, I was taking advantage of, there were a lot of research reagents that were made available. They were developed within academic groups and then made available freely to the academic community. I think a lot of times we, as part of a company, we needed to pay some kind of access fee or whatever to get to them. But they were the kinds of tools that there's no way we could have developed them ourselves. It was only in an academic environment and over a long period of time that these things could be developed and then made available. So, and typically those labs are very dependent on federal funding. There are other sources of funding, but I would say the majority of the time that kind of work is done with federal funding for the really basic research.
Yeah. So I guess what's at stake then when we consider, whether that funding is going to continue and to what extent the United States is going to continue trying to lead in these, at the bench in these labs?
It's a challenge for sure. The United States has always been such a leader in basic science in all different fields. And I personally, of course, would hate to see that diminish. I think what I sense is that people are certainly trying to come up with, alternate ways of remaining as productive as they always have been. But it's challenging. It's a significant shift in the way people can support their work. And ultimately, I think that will hurt U.S. science in the long run. But, time will tell, I guess.
And finally, Dr. Brunkow, do you have a sense of how this is going to change your life and the trajectory of your career yet?
I think it is going to have a change, and I'm still trying to get my head around what that might be, what the outcome will be when the dust settles a little bit. I'm very excited about the prospects of what kind of opportunities may come my way as a result of this, but I can't tell you at this point what that's going to look like.
Well, we'll be excited to keep tabs on you.
Well, thank you.
Well, Mary Brunkow is the Senior Program Manager at Seattle's Institute for Systems Biology. She's also a UW alumna, and she shares this year's Nobel Prize for Physiology or Medicine. Dr. Brunkow, thank you so much and congratulations.
Thank you. It's been a pleasure.
Thanks for listening to Soundside. This show is only possible because listeners support us. If you're able to give right now, please check out the show notes for a link to donate. And don't forget, you can listen live on KUOW 94.9 FM Seattle at noon and 8 p.m., Monday through Thursday, or anytime online at KUOW.org.